Okay, so we look here at regression tests. This is another way to tell if results are statistically significant. Um, but quickly before that, a note of caution with scatter plots, something good to think about. And it's an example from history. And the Challenger explosion back in the 80s was caused by a failure of an O-ring associated with the fuel system. The scatter plot to the left shows the result of failure rates of repeated testing at different temperatures. The issue here is at the time of launch, the temperatures were below freezing. It was 30 degrees Fahrenheit approximately when they launched that day. So based on the scatter plot above, we can see that that's problematic because uh, they never accounted for temperatures that low. The lowest they went was just slightly over 50 degrees. And here's what the problem was. They figured since they had this set of data, they could they figured, hey, we've got this set of data. We can kind of extrapolate what's happening. And so you can see, if you see that red line at the bottom, that's right. You can kind of see what my pen's following along. That's kind of what the NASA engineers, the rocket scientists, if you will, assumed that they're going to follow this linear pattern. Well, the problem was that this data wasn't linear at all. In fact, when they went back and they started looking, they saw that it's actually this black line that my pen is following right there. It's actually more of an exponential model. So the probability of a failure went up pretty significantly. The warning here, the caution I'm going to throw out at you, is something we can learn from these people. When you try to go beyond basically the scope of your data, that's called extrapolation, and that's very tricky if you don't do it properly. Right? So when you're going to make predictions using a line of best fit and scatter plots, you pretty much should predict within the range of the data that you're given. So they could have made a prediction, if you look back over here, like let's say it was 60 degrees. They don't have any data on 60 degrees, but considering 60 is well within the range of their data, they could have made that call. Okay, so really quickly, what I've done, I put this data into the calculator, and we can set up a situation and figure out, right, does the number of beers somehow, is it related to the blood alcohol level? Right, so if we put that into our list, right, we can create a scatter plot. So go down and we'll turn list 1 on, so second L1 versus L2. This is one when you push the zoom button, you go down to zoom stat number 9. We can see, hey, that does look like a strong positive linear relationship. Maybe a potential outlier sitting here, right? If we had to describe the relationship mathematically, that's just where we come over here. Remember, we go down to number 8, get the line of best fit. So again, make sure you use the list that you've got set up. And so our line of best fit, negative 0.0127 plus 0.018x. There's your coefficient of determination, right? So 80% of the variation in blood alcohol level is explained by the number of beers. That R kind of confirms what you can see in the graph right there, that it's a positive, strong linear relationship. And then we can also interpret slope and y-intercept. We've been pretty good at that. Now, if we wanted to, we could go look at the residual plot, right? So far, we've seen the actual graph. We've seen the R value. Everything makes us feel like it's pretty linear. And so, right, we do L1 versus, if you hit second list, since I've done the line of best fit, I've got the residual sitting there. And now go back to zoom, push number 9. Now we can see there's a good scatter. There's not really a pattern. So this looks like a good residual plot. Maybe a potential outlier here, and that's that same outlier, but not enough to make me really concerned with it. Well, what we're going to look at here with the testing, right? It's just another way to kind of to interpret whether or not we actually have a linear set of data. So the first thing is to get this thing started, if a set of bivariate data was going to have no relationship, we'd probably expect a scatter plot. We wouldn't see any positive trends, negative trends. It'd do something like this. It'd be just kind of all over the place. And the line of best fit with that would just be a horizontal line. And remember, back in your Algebra 1 days, that would be a slope of 0. So a slope of 0 is associated with no relationship. Now, we've seen this before, right? This idea of relationship, tests for slope. We're going to use these to determine if a linear relationship exists, right? If you took out the word linear, is there a relationship, Remember that was a chi-squared test for independence, right? So we're going to actually run a test, but this time we're going to use the slope. And really what we're doing is the slope different from 0? In other words, if there's a positive relationship, that we'd see a positive slope. If there's a negative relationship, we'd see a negative slope. Or, if there's no relationship, there's no slope. All right, the sample data in the equation that we just found, right? Think about the blood alcohol level we just did. It's sample data. We can use that to estimate a true value. So this sample equation, this is what we're really good at. We can go find that pretty easily in the calculator. There's some actual true equation if we could collect the best possible data that would accurately predict the blood alcohol level perfectly. That true equation is out there, but it'd be really, really hard to find. So what we're going to do is use our sample data to try to figure out what is really close to this perfect, this true value of the regression equation. Right? In order to do that, that's where we're going to set up this test, right? So the hypothesis, think back about your chi-squared test for independence. Your null hypothesis was that they were independent. And another way to think about that was no relationship, right? And then the alternative was that they are not independent. Or another way to say that there was a relationship. So here's the thing. It's the same type deal with this null. The slope is 0. Think back about what we just said. If the slope of the line of best fit was 0, right, that meant the scatter plot was all over the place. There was no relationship, right? We're saying the null hypothesis, no relationship, just like we did last unit. The alternative then is that there is a relationship, right? That there is a slope, that there is a relationship. There is a relationship. Now what's interesting here, these are the two that you're most likely going to use. But every so often you might see something that asks, is there a positive linear relationship? So then you test to see, is the slope greater than 0? Or there could be a negative relationship. You test to see if the slope is less than 0. So the thing is, it's going to be one of these three alternatives. It won't be all three. Typically, your null and alternative are the two in the box. But every so often you might see the question would ask you, is there a positive linear relationship? Is there a negative linear relationship? So this is called a t-test for slope. Your four conditions. Is the data linear? Here's the random, right? There's your SRS. And then equal variances. Is there scatter around the line consistent? A good place to look at this would be the residual plot, right? Are there positive and negative values of the residuals? That tells us that there's values above and below the line of best fit. And the errors are normally distributed. So that's kind of a funky one. And we're pretty much going to always assume that that's true. I'll show you how to do that in just a minute. Your test statistic, B. This little b is from that. That's from your least squares regression line. We know how to find that. The alternative, or the null hypothesis, remember, always said that there was no relationship. The b equals 0, so that's 0. And this is what's called standard error of the slope. And that's essentially, it's a form of the standard deviation. Okay? There are 2 degrees of freedom associated with this test. Right? So this is another form of degrees of freedom. It's a little bit different. We're going n-2 because there's 2 variables, right? It's bivariate data. So let's look at the previous example with, is there a relationship between the blood alcohol level and number of beers consumed? So we're going to run a t-test for slope. The hypotheses right there at the bottom. So the conditions. If we went back and we looked, right, here's kind of a split screen of what the line of best fit on the scatter plot up top and then the residual plot. That tells us a couple things. One, it looks like it's pretty linear. Look at the scatter plot. Random. It was actually told that we were randomly collecting this data. Equal variance. So look at the residual plot. You can see it right here. That's pretty consistent scatter. And then this last one, the errors are normally distributed. What you could do in your stat plot is you could create a box plot using your residual list. And that's all that I've done right there. I'm going to see what that looks like. You just go to second stat plot. We'll just use that first one. Why not? We'll go down. We'll go create box plot. The only list we just want the residual list, right? And then we don't want to use that. Then graph. Whoop. Might help if we zoom 9. So you can see that box plot, there's not any like strange outliers, not a really funky whisker or really strange looking box. So it's safe to say this is normal. Typically though, guys, honestly, we're just going to assume that those things are all true. So as long as you know them, we're, especially number 4, we're pretty much going to say, hey, errors are normal. Residuals are normal, and we're good. Remember too, errors, that's just another name for residual. The actual test, where are all these numbers coming from? Well, I'll show you in just a second. Right, this was from our least squares regression line. If you go way back, that's always 0. This is a number that our calculator actually won't give to us. This is a different type of output, but the calculator will give you 7.48. The probability, the p-value, this might look a little funky to you because we haven't done anything quite like that. So we won't typically write it that way. We'll just write the p-value is essentially 0. Again, I'll show you where that's coming from. So what that tells us, right, is now we'd say, all right, so at an alpha level of 0.05, 0 is less than 0.05, so we'd reject the null. And then it appears the slope is not 0. Evidence suggests that a linear relationship exists. Between blood alcohol level and number of beers consumed. All right, so how does that work with our TI 83s and 84s? All right, so let me go back and look. There actually is a t-test for slope. If you go stat, over to test, way down at the bottom at F, you have a linreg t-test. That's our t-test for slope. We've got our data in list 1, list 2. You can see right here, this section right here, that beta and this P. We don't deal with P, but your alternative tells you which one of these to pick. We decided that we're just going to test not equals to. In all honesty, that's probably the one that you're going to pick anyway. But right here we can see there's your t-value, 7.48, as we saw in the slideshow. You said the p-value is essentially 0, and if you look, 2.969 times 10 to the negative 6, that's 0.000003. That's essentially 0. Here's your information on line of best fit, negative 0.013. There's your B, 0.018. You scroll down, you get your R squared, your R. Here's basically at the bottom, the A, the B. S is a little different. You guys don't quite know what that is, so don't worry about it right now. But you get your output from your line of best fit when you did linreg before there too. But in addition to that, when you ran the test, you get the t-value and the p-value as well. Now, just as a heads up, because this is a t-test, that's why we use t right there. Remember when we did a chi-squared test? When we did the formula, we had chi-squared equals something minus something squared over something, and we added those all together. The chi-square test did chi-squared equals in the formula. Since this is a t-test, we use t. So using data output is the one last thing to make sure we're aware of. So a lot of times you guys have been seeing, and if you look through your Frappy packet, you get a ton of these data output tables. And you can actually pull your line of best fit directly from this. The top line is always your intercept line. Sometimes it's labeled intercept. Sometimes it's labeled something else. But the top line is always the intercept data. The bottom line is always your slope data. So what you can do, if you look at that first column, that's always your least squares regression line if you put stuff in order. So here, for this output showing the relationship between waist length and your weight, is there evidence to conclude that there's a linear relationship? So here's your line of best fit. Y hat equals negative 0.3619 plus 1.28. And so from here, you could do your interpretations and whatnot, right? You could also actually end up running a test straight from here. So remember, is there evidence to conclude that there is a linear relationship? It doesn't say positive, negative, so here we'd be testing the beta equals 0 versus the alternative beta is not equal to 0. So here's our formula. Little b, that's sitting right here. Big B, we set it in the original, that's 0. And then the standard error for B, right, there's the word standard error. And remember, this line right here is everything you need to know on slope. So we can literally plug all of that stuff in, right? Well, strangely enough, if you actually do this math, it's 10.15, but you didn't actually have to do that math. It's sitting there. The probability, the p-value for this is sitting there as well. P-value is essentially 0, and that's coming from that last part of the line. So you can essentially run your whole t-test, right? And now we can say that 0 is less than 0.05, so you'd reject the null. And evidence suggests then that there is a linear relationship, right? The alternative here, just like last unit, that there is a relationship. Right? Now, one quick note, we don't use the top line here except to find the line of best fit because nobody ever runs a test on the y-intercept. And that's simply because so often the y-intercept has no practical meaning. So that's how you can run a test using the calculator. And with the data output, chances are you guys are probably going to get the data output. You're probably going to get this table more than likely and have to run a test out of there, which is actually a lot easier for you guys. As long as you know how to read it, you'll be good to go.